the day. Malta's next. Sorry, I've caused us to overrun slightly. Apologies to Gunardi. I do apologise. We'll hopefully get to the break on time. Okay, the next speaker is Malte Peter, who needs no introduction as well, and you're talking on a related topic, water wave interaction. Over to you, Malte.
Right, so yeah, thank you very much for the introduction. Thanks to the organizers for allowing me to be here again. Very happy to be back in Cambridge. And also like to thank the EffectFact project for supporting this work. This is sort of a bits and pieces of a few things, but mainly, and I think this is very appropriate, on a paper jointly with Mike Smith, Dave and Mike, that basically started during the program, the Wiener-Hopf program, in 2019, I think it was, yeah. And so I'll report on some of that. And also what's very very good is that Mike basically gave an awesome introduction to a lot of stuff that I'll be talking about, although no piezoelectric effect, but the mathematics is quite similar. So the main difference though is that I want to talk about submerged plates. Otherwise it's quite related. And towards the end, and this is also there's some analogy to what Mike was saying, that when I was asked if I want to come here and report on some recent work on Wiener-Hopf problems, I thought, oh, this is perfect. We've just started working on these two plates problems. By the time I'll be here, I'll be able to report on that and show some great results. And as it turns out, I'll get to that. We're not as far as I hoped when I submitted the abstract. But anyway. Okay, so just Mike's already hopefully convinced you that horizontal plates in water are a very important problem and need to be understood better. What my main motivation or the main kinds of plates I'm looking at today are poroelastic plates or poroelastic plates, and the motivation there is a bit different. One thing where they're used quite often is as wave absorbers in wave flumes and narrow wave tanks. So it's basically you have a wave tank, you have a wave maker, you have some object that interacts with the waves that you're interested in, but then the problem is your wave flume is not infinitely long, so there will be some reflection off the end, and that is typically something that pollutes your experiment. And so what you want to do is you want to absorb the wave energy, and one way of doing this quite commonly is to install a porous plate. Also, you can do this on a larger scale as breakwaters near coastlines. So that's where the porosity comes from. It's for dissipating the wave energy, and if the plates are long, then they're likely to show elastic behavior, and then you're talking about poroelastic plates. There is a bit of an aside here, which I think is quite appropriate to talk about this here as well. And this is about floating viscoelastic plates. It's slightly different from what the talk's about, but closely related. And also, since Mike talked about the floating plate, and he showed these nice photos of the marginal ice zone at the beginning, this is basically where this relates to. And I think it's very appropriate to report on this briefly during the introduction, because I spoke on this stage, I think it must have been about 1.5, 2 years ago, precisely on this problem. And I sort of said, well, if you do a back of the envelope calculation, it looks like this is going to happen. It turns out a master's student looked into this in more detail last year, and she found out it's actually not that simple. And I'll briefly report on this, and it's also a great introduction, I think, to porous plates as well. So this is about floating elastic plate, and this is a common model for ice flows. And so there is some work where field data has been analyzed, and it shows that there's a certain frequency dependence of the attenuation rate on the frequency, which is omega to the cube at leading order. And you can see some accumulated frequency, some accumulated field data here on a log-log plot. This the attenuation as a function of frequency, and you see that roughly the exponent is typically about 3. And so if you look at the dispersion relation in infinite depth, it always has this form in this context. And if you then do a perturbation analysis around the open water wave number, which is just frequency squared over gravity, and you do a calculation, then it turns out that the attenuation rate, which is the imaginary part of the wave number at first order, is this thing there. It's negative the imaginary part of k0, which is omega squared over gravity, times this q thing, which is part of the dispersion relation. And if you do that, you can do that very nicely for different models. So if you just by matching the water pressure to the plate pressure, and then you can plug in different plate models. For instance, if you just take the classic Greenhill model, basically the plate equation, very, very similar to what Mike's shown, except that the coefficient here for me is just real. For this case, then you can compute this Q just by a simple algebra. You stick it into the formula, and you can compute this attenuation rate. And it turns out, because there's no imaginary part here, the imaginary part is 0, so there's no dissipation. That's not surprising, because this is a fully conservative model. You can do that with other models. For instance, you use this Robinson-Palmer model. You stick that in, you get this extra term there in blue, which is a first order time derivative. So that gives you, in the frequency domain, gives you an imaginary part. You see that there. And then you, again, stick that in. And remembering that you've got to multiply with k0 squared, this thing, then the imaginary part, gives you an omega here, an omega squared from the k0, and that gives you omega to the power of 3. And in all of these cases, you've used the standard kinematic condition. Now, if you want to introduce porosity, the kinematic condition changes to this, where you get this additional term, where this p tilde is the porosity parameter. Okay, so now you can do the same analysis, and this is basically where back of the envelope calculation it looked like. You might end up with something like omega 3 again, which sort of suggested that this might be a useful model for wave attenuation in marginal ice zones. Turns out, if you do this properly, and this is this master thesis of Mang and Langenmeyer, turns out that actually what you get if you do this properly is omega to the power of 1. So the dissipation is actually too strong. So if you just take a porous plate, this is too much, and this has been sort of sparked some ideas of trying to look at this slightly more realistically by saying actually what you have is you have to incorporate this multi-scale behavior in a much more detailed way. So realizing that actually what you have is you don't have just one big piece of sort of porous plate, but what you have is you have chunks of ice, and then you have waves or energy being dissipated basically in the gaps between the plates. So, but this is of course more difficult, so it's not that simple. But again, this is also, so as I said, this sort of, like 3-4 minutes. So two purposes here of my introduction. First is to again show you that porous plates are important, but also sort of report on this, or sort of clarify this sort of vague claim from about 2 years ago. Okay, so for the rest of the talk, I'm interested not in the floating plate, but that submerged horizontal plates. Okay, so there's different solution methods, quite standard. Most prominent probably eigenfunction matching, or you can use, if you want to, sort of numerical methods. You can use coupled boundary element, finite element methods, and I mean generally they work all right. But typically they are computationally expensive. And also there's a bit of subtlety here, is that the eigenvalue problem, so if you think of eigenfunction matching in the plate region, may not be self-adjoint. And that's closely, of course, related to the dispersion relation, which may have multiple zeros and might be quite tedious to solve. Mike discussed that for the piezoelectric floating plate, but it gets worse. These kind of problems if the plate is submerged. And the other thing that can be a bit of can be a bit annoying is that the eigenfunction matching is rather slowly convergent. If you're just interested in sort of rough answers, or you have a really big enough computer, that might not concern you too much. So the method is still quite useful, but it can be an issue. Right. So what I want to talk about now is submerged porous and poroelastic plates, and of course I want to solve this using the Wiener-Hopf method. Okay. And I do want to use, Dave, as we did in the paper, use the Cauchy integral method for the factorization, because that doesn't require knowledge of the roots. Okay, and I should mention, Mike, I think, mentioned a few of these works. So there's a bit of stuff on floating elastic plates. So for the conservative case, not the piezoelectric one that Mike talked about, by Yuk Chung and Colin Fox. The paper has been mentioned, but also there's also a follow-up work by Chris Linton and Yuk from about 20 years ago, and then the entirely porous plate also did with Dave Evans quite a while ago. Mike's done some work on the elastic version of that, and so the main contribution of the joint work I'm presenting today is basically the realization that more or less it's all the same if you interpret it in the right way and sort of write it all in the right way. Then you see that it actually doesn't make much of a difference, and you can formulate all of these problems in quite the same framework, and basically the solution method is quite generic. And that's what I'll be talking about today. So yeah, to be a bit more precise, so what am I looking at? It's basically the same framework that Mike discussed as linear water wave theory. So assuming inviscid, incompressible irrotational flow. So I'm working with a velocity potential, and I look at time harmonic motion. So I have the complex potential, and I just look at, so it's basically a 2D problem, the third dimension. I just look at, take into account by concentrating on obliquely incident plane waves, so I can also factor out the, well, in this case, the other horizontal coordinate, the y coordinate. So in the end, I just have an unknown depending on the horizontal coordinate x and the water depth coordinate z. And then, so just to save a bit of writing, the next few slides where I will always talk about the porous plate, but I'll discuss how this very, very easily through the way we've done the analysis generalizes to the poroelastic plate afterwards. But so just for the geometry here, so I have my plate, it's flat, it's thin in the domain x greater than 0 and submerged to a depth minus d. Yeah, and then basically the water domain is just the rest of the strip between depth minus h. Water surface, still water level is at 0, and otherwise it's yeah, it's this infinite strip. And the porosity properties, that there's reasonably classic models how to incorporate that space. You can all encode it in a parameter sigma, which is complex, where the real part is related to the friction. There's basically Darcy's law involved in that. So that's basically where the actual sort of geometric porosity comes in. And then there's also, if you want to take into account the inertia, you can do that through the imaginary part of the sigma. And if you do that and you write down the problem through for these obliquely incident waves, you end up with Helmholtz equation. I mean, this probably comes as no surprise to you. You get your bed condition, no flux through the seabed. You got the open, so at the free water level, at the free surface, you get this dz phi as alpha phi, with alpha being omega squared over gravity. That's the open water, what I call the open water condition in the introduction. And then at the plate, you have these two conditions: the velocities. The velocity has to match independently if you look at it from above or below, and that is proportional to this jump term, I mu jump of phi across the plate. And the jump you see down here, and what is this mu? This mu is this porosity parameter sigma, But you can see here, and I've hidden that in the mu, it is frequency dependent. So just as this is not surprising, of course, but basically through this derivation, the omega pops out explicitly, and you have this linear dependence on the frequency here. But that's for the rest of the talk, that's hidden in the mu. Okay, and of course what you have, because you have your plate at the tip of the plate, you have this square root singularity that you have to be careful about with the submerged plate. Okay, so what I want to do now is just basically the same way that Mike presented. I just look at the incident wave coming in from the left. I know what that looks like. I have my open water dispersion relation with the one negative imaginary root and the positive real roots for the evanescent waves. And if I do that, then I realize this kind of classic wave solution with this vertical dependence psi satisfies the Helmholtz equation, the bed condition, and the free surface condition. And so wave of unit amplitude has this form. And what I then look at, I just look at the in the end, what I want to do is just look at the scattered potential. Particular to the left-hand side, I have my incident wave plus the reflection, and what people are typically interested in is this reflection coefficient R infinity. And in the plate region, it's really just that the far field condition is basically the porous plate, the poroelastic plate, dissipates the wave energy, so the potential goes to 0. Okay, so what do we do with this? Is I now split the potential in the part basically below the plate and above the plate, but I do that through the whole domain. So even if there is no plate, I basically virtually extend that to the left. And those are then I have this phi 1, phi 2, and a Fourier transform just in the standard way. And I also hope I get I have the same signs for the phi plus and phi minus as Mike did, so that's a good sign. Or we just copied and pasted from the same paper. But anyways, I don't think I need much to say about this. And of course, also as was I think it was Raphael's talk yesterday. Of course, what we have to do is add a small imaginary part for now, and then we'll let that go to 0 in the end. Okay, so I'll spare you the algebra. It turns out that the Wiener-Hopf equation, if I do this all properly, looks like this, with the kernel k, and basically my unknowns d plus and q minus with the respective analyticity properties are basically the jump in potential at the level of the plate. And these normal derivatives, which from the boundary condition are known to be the same. And what I have is the kernel has this form, and this is very generic for all of these problems. If you look at this very closely, what you see is that in the numerator you have the open water dispersion relation for the whole depth, and in the denominator. You have a product of the dispersion relation underneath the plate or above the plate, and then you have this imaginary part here where the porosity parameter comes in. Remember, the mu depends on frequency linearly, and what you have there, and it's multiplied again by the open water dispersion relation. So that basically doesn't see the plate part. And depending on how familiar you are with these problems, you might think, oh, this is I've seen this many times before. Basically, the kernel reflects these dispersion relations. That's really also part of the key to being able to do all of this in a quite a unified framework. Okay, so what do we have to do? Well, this workshop, I think I don't need too much to say about this, so we have to be able to factorize this in a k plus, k minus regular in the respective parts of the complex plane. And if we can do that, then of course we we split the equation into left and right hand side, being regular in the respective parts of the complex plane, the respective half planes, and then in this case, I don't have a polynomial to worry about if I have the porous plate. If it's a poroelastic plate, then I'm basically in quite a similar setting where I have to worry about this polynomial. I'll get to that in a few slides. Okay, and then basically, but yeah, in the end, either way, it's Liouville's theorem, right? Okay, then from that I get the equation. Well, these are the expressions, and I can read off the reflected wave from the inverse Fourier transform from the integration, and the reflected wave arises from the simple pole at S is equal to kappa, the open water wave number, and then basically you get this very, very nice and simple formula. Okay, so we can split this using the infinite product decomposition as in Mike's talk. But we run, and basically we run into the same problems. If we have the porous plate or the poroelastic plate, the problem is that the dispersion relation has this, as we saw, has these complex contributions, and they make it very tedious to track those roots. You could do that exactly as Mike showed, but it's there's a nice way of doing this here, which Dave's already mentioned, the Cauchy integral method. Basically, what you do is you take your function that you want to factorize, you split it into something that you can nicely factorize, and something that has this asymptotic behavior going to 1 for large argument, and then basically you just use the Cauchy formula. Right, and if you do that, you just compute this, and using the asymptotics, this all works very nicely. I presume some of you are familiar with that. And so if we do that, we arrive at this formula here, where again just focusing on the reflection coefficient, which is this exponential with this function theta depending on k, and the expression is given here. Right, and I think yeah, no, that's all good. Okay, so what do we have to do if we want to do this for the elastic plate? And basically the short answer is it's exactly the same. Just a few reminders. As I said, there are a few things on the elastic plate around, and there's also an eigenfunction matching solution. But with this framework that I presented, this is basically now just a very, very mild modification of what I've shown you. So the only thing that changes, of course, is the condition with the plate. So so this condition here becomes this one down here involving the plate equation. You see the fourth order derivative there, and I've already substituted the potential in there. So instead of the plate displacement, you see dz phi appearing. And then we have the edge conditions, which typical ones are either clamped or free, and they're of course conditions on the derivatives of the displacement. But then if I express that in terms of the potential, then this is what it looks like. And if you want the poroelastic plate, you have to do what I showed you in the introduction by also modifying the kinematic condition. And then you get this imaginary part appearing in here as well. So what changes? So I could just basically go back and go through the whole analysis again. The only thing that changes is the following. Well, first of all, of course, because I have these other conditions, they change the dispersion relation. So that changes my kernel k. So for instance, for a submerged elastic plate, the k is now this quotient there, where again that doesn't change. On the numerator, we still have just the open water dispersion relation, and in the numerator we again have something with the open water dispersion relation, which is then sort of corrected by sort of the other sort of implicitly appearing dispersion relations, which again is the dispersion relation for underneath the plate, the dispersion relation above the plate, and then instead of having this this complex term here, if I just have the elastic plate, I get this polynomial in front of that. So again, very similar structure. Yeah, so this one here for the non-porous part, this is again has two positive real roots, pair of complex roots, and infinitely many purely imaginary roots, and it becomes, you can sort of already guess what it will look like if I also add porosity. Anyway, the one thing that I have to be slightly careful about, if I have elasticity involved, I have exactly this thing that I get these two additional unknowns from the edge conditions. So I have to do this additional step, as Mike described quite analogously here as well. Okay, yeah. So I also have two videos just to show it using precisely doing precisely what Mike did, i.e., computing the single frequency solution for a number of frequencies, and then just assembling that in exactly the same way. Through the inverse Fourier transform, and I also just have an incident wave pulse, because then the contribution of each frequency to constitute that solution is very simple. And so what we see is we have this Gaussian pulse coming in from the left. You see my submerged plate down here. Yeah, and what you see is the free surface displacement. Let's look at the video. And remember, because I have the submerged plate, what is quite interesting or slightly special compared to the floating plate is I actually have two propagating plate modes. But you can see how the wave is transmitted into the plate. You see some reflection. And you see these two plate modes, one which is at different frequencies, and so one is more, because the water waves are dispersive, one is moving much more quickly than the other. So I think this movie should probably stop soon. And I have another plot. So this was for the elastic plate, and of course with the Wiener-Hopf solution, this takes like basically no time to compute. And for the and I'll just show the same movie now, but so it's basically everything's the same, except that you'll eventually see that there is a red line as well, and one is precisely the same as before, and the other one is for the if I add porosity, and now you can guess which one is which. Well, the porous plate, of course, dissipates energy. So the dashed red line is the one for precisely the same movie as before, so without any dissipation. And what you also also quite similarly see, because the wave is just reflected by the edge, the reflected wave doesn't really care too much if there's porosity or not. But the other one, you see the dissipation, and you see the frequency dependence of the dissipation as well, very nicely, which I've explicitly built in. Right, and I've really used up my time. It took a bit longer than I expected. So I'm not going to talk about the two submerged plates. There's some joint work by a former PhD student of mine on different versions of this with Dave and with Gennady, also using different kinds of solution methods. But unfortunately, because since he's left Augsburg, he's been quite caught up with other things, and so this is progressing a lot more slowly than I hoped for. Anyway, I'll spare you the details. Because we have the formulation with the matrix kernel, but we don't have the solution yet. So maybe I should really, my time's up, stop here, and just thank you very much for your attention.
Thank you very much. Okay, as you started slightly late, I'll let you have one question.
Thanks. Yeah, sorry for running a bit late.
I can ask.
Sure, John.
All the time. You made a reference to the fact you come across a non-self-adjoint problem.
Yeah.
Now, I do know that in stability theory, this happens all the time. And they simply introduce the adjoint operator.
Right.
And off they go. You have orthogonality between the adjoint functions and the original.
Yeah.
So is there any reason not to do that here? Is it harder? But it seems to be cultural. We just don't
Yeah.
very often hear about it. But you certainly do in
Yeah.
stability theory.
Well, you don't really have to. If you do it the way we've done here, you don't really have to worry about it. So this is another way of getting around the problem. But it's actually a good point. If you encounter that, I haven't seen that. So it's a good point.
It's
Yeah.
a lot known. I mean,
Yeah.
it's essentially almost completely known, the basic theory.
Right. No, thanks.
Okay, we better stop there and move on. Thanks again, Malte.
Thanks.
Excellent.